For me, it's roughly the same. I mean, it's yet another language for me. Exactly, yeah. Next time we'll make it in Italian. Okay, so thank you very much for having me here. Last presentation, so I'll try to keep it upbeat and hopefully interesting. Exactly. So hopefully you find the logo already cool, but to tease you even more, well, let me show you this. Does this motivate you enough, okay, to learn more about this talk? This happened a couple of days ago, in fact, 1 week ago in Indianapolis, and you can probably spot very nicely on the car, which is a Dallara, manufactured in Italy, not one, but actually 2 logos that are built by our team, okay? And one of those is Zenoh, which we'll talk about today. The other one is Cyclone. And all of this is technology made 100% in Europe, okay? So what is this being used for? That's what we're going to discover in this talk. Ready to go? Let's go. Okay, so before getting to cars, which is exactly where I know you want to get, let's try to understand what was the problem that we wanted to solve. So I didn't introduce myself because, I mean, I always assume that people know me, but that's not always the case, so sorry for that. But so Angelo Corsaro, I'm CTO for AD-Link, and I've been working in distributed system for, almost since people used to call me a kid. Okay, so some of the systems that I've built and designed power things that are in the NASA Space Kennedy for launch system. I was one of the guys that worked with the Pasadena lab for the Mars rover, and European traffic control and management runs on some of the software I've also written and architected. Okay. As I've been working on communication technology for a long time, there was something that was giving me pain, and not only giving me pain, but giving pain to our users. So to understand what was giving me pain, let's try to imagine that we are data for a moment. Okay, so data is produced, then at some point after production to do something, we need to distribute this data. And then usually we distribute data. Why? Well, because either we want to compute, or perhaps we want to store this data, right? But actually, after you've computed something out of this data, what do you usually do? Well, you distribute this data again, and perhaps you store it again, or if you had stored data, eventually go and fetch back this data to do something with it. And so far you say, okay, so what's the problem? You might think there is no problem. So let's go one step further. If you look at how we deal with data in movement and data at rest, I mean, it's always data, right? But we have 2 different classes of technology for dealing with these 2 different aspects of data. We have, pub/sub technology, which is the standard de facto for moving data around that we use for moving data. And we have database technology for actually storing data. And everyone thinks, yeah, that's logic. But it's always the same data, okay? So that's how the ecosystem has evolved. And, we give this for granted. And something else that is also, interesting is that data in movement, we assume that it's okay to have it pushed all the time. So most of the pub/sub technology really push data. And when data is at rest, the same data that was moving before, now we have to pull it. Fine. But there is, things start getting a little bit more complicated when you start reasoning about location transparency. What is location transparency? Is the ability of consuming data without knowing who or where this data is produced, right? If you're using a pub/sub technology, you subscribe to a topic, you get data, you don't care who produced that data. But then, if the data unfortunately gets stored somewhere, now all of a sudden you lose location transparency. You need to know the database in which data is stored. Is either that database or that database. And this is actually okay if you have one database, or if you are a big fan of the cloud, so you have centralized architecture. But if you look at where we are going with decentralization and the kind of application we work with, more and more you have the need to decentralize computation, decentralize storage, and as soon as you decentralize storage, the question is, okay, how am I going to fund my data? Because I have no location transparency. And solving that problem, which is a problem that, we've been struggling for years, it's done by duct taping or bricolage, okay, if we use some French. And so if you look, as I mentioned before, decentralization, the situation gets very complicated. Now, fog computing, edge computing, you name it, is very in vogue. I prefer to think about a continuum from cloud to device. And the question is, how do we build technology or that really allow us to abstract from the location of data and allow us to deal in a unified manner with data in motion and data at rest. Because this is what we really need, okay? And I mean, this was a big pain for me. It was a pain, and at some point, actually, I was running a standardization working group on a distribution technology called Data Distribution Service. I said, enough, I need to work on something. We need to solve this problem. So with the cream of the crop or some of the key members in our team, we decided to tackle this problem, and we came up with a new technology called Zenoh, okay? Where Zenoh stands for, well, there are really two references. Zero Network Overhead Protocol, but then it really also tried to recall, if you remove the H, that Zenoh, philosopher and mathematician from ancient Greek. And I'll let you understand eventually why. So what we did in Zenoh, and we didn't get it right at the first shot, right? We iterated a few times. But what we tried to do is, okay, can we find the minimal set of primitives that can allow us to express data in motion and data at rest? And the answer is, eventually, we found, and as you'll discover, we only need 4 primitives. Nothing more, nothing less. And I'll get to it. And by doing it, we realized, actually, that with those 4 primitives, we could express data in motion, data at rest, and actually computation. And patterns like computation replication, computation of data, or even workspace like MapReduce were all expressible as part of our 4 primitives, which is very powerful. And we'll get to that in a moment. Now, something that I don't have much time to touch upon, but that was a big concern for us as well, as I said, we focus on the continuum from the cloud to the embedded device. So we wanted to have a technology that could scale out, but also scale up and scale down. So be able to run on very constrained devices and on very constrained network, okay? So as such, we structured Zenoh as a protocol that can run on top of layer 2. So we don't need to run on IP. We can run on IP. We do our own routing, okay? And our routers are soft routers, but the performance are quite terrific. But why do we need to run over level 2? Because sometimes IP is too much. And and sometimes we actually don't have IP either. So we have a protocol that doesn't assume that you have IP. You just have a best effort level data link. That's enough for us, okay? And then in terms of the key protocol highlights, I need to go a little bit quickly because we have quite a bit of material to cover, but there are plenty of presentation online. The protocol is extremely wire efficient. If you look at the wire overhead, we have 5 bytes wire overhead on top of your data, okay? How do we do that? Well, I give you a quick example. What is the right sequence number resolution for a protocol? There isn't one, okay? Because all of the existing protocol fix a sequence number because they had fixed one deployment scenario. And as we need to run on something that is like an 822.15.4 or a ZigBee, where you have 127 bytes MTU, as well as over a satellite link, the 2 scenarios are very different. In one case, I can't afford 4-byte sequence number because it's too much, okay? And I don't need it because I don't need to manage packet in flight. On the other case, I need to have as many packets in flight because I have a network that is high latency and high throughput. So one of the things that Zenoh does when establishing a session, negotiate in between other things, the sequence number resolution. So that depending on your network, you can get 1-byte sequence number resolution or up to 64-bit, okay? So there are lots of tricks played in the protocol that allow us to have this magic number. And with 5 bytes, I mean, arguably we are the most efficient wire protocol on the market. That then provides the kind of high-level feature that we have. In terms of topological support, we can do peer-to-peer communication, okay? So you don't need an intermediary. And as we have a routing protocol, and the same protocol can route, you communicate, as I will show, over a fully connected graph over an arbitrary mesh. And you can have, obviously, a network of routers deployed on the backbone. Other important things, if you have a very constrained device, then they can run as client. In that case, they don't have the burden of peer, because a peer is always able to route data for other peers. And we have use cases with some very cute maritime robots that are used for oceanographic exploration, in which you have these little drones, some of which are very, very constrained and can't afford to run the full stack. And so they just pair up with the closest peer, and the closest peer mesh up with other peers, so that's how they communicate, and eventually someone has an uplink to the back office, okay? So our stack, I didn't mention it, but you saw it maybe on the title slide, is open source. So it is run as part of the Eclipse Edge Native working group, of which I'm actually one of the founder and still one of the member of the steering committee. The entire stack is written in Rust. By the way, the first version of Zenoh was written in OCaml. We are in France, yes, okay? We love OCaml, but we moved away from OCaml for a very simple reason. Multicore OCaml didn't come when we wanted and isn't still there yet. So, C for us was not an option. We have done C and C++ in the past, not as sufficiently productive, too dangerous for systems that you want to be secure. So we couldn't afford anymore to use OCaml, and we moved to Rust. But then we provide language binding for lots of targets. We have an embedded version, that's the only C code that we have, called Zenoh Pico. And here you see Zenoh Pico in action, the little animation. But you can run Zenoh Pico on Arduino, you can run it on ESP boards, Zephyr was mentioned before. And that's an example of an end-to-end Zenoh application. Zenoh is running on the little gyroscope, it's running on the robot, and so on and so forth. If we talk about wire efficiency, well, actually, I'll jump that slide. Let me, as I teased you with the India Autonomous Challenge, let me explain you how it was used in the India Autonomous Challenge, and then we'll get to the abstraction. In the India Autonomous Challenge, and this is a common case for Zenoh, Zenoh was used for everything that is V2X. So it would use for teleoperation of the car. So I have a video in which you see a guy with an Xbox controller driving the car. Those interested I can show you after my talk. But in general, we were running over a CARB, which is a Cisco spatial Wi-Fi network. We had 1 megabit per second per car, and we have the limits that we couldn't send more than 127 packets per second, and packet couldn't be bigger than 512 bytes, okay? So it was a rather constraining environment, and all the teams that were competing in the India Autonomous Challenge, they were free to select whatever they wanted. All of them, all 17 teams, ended up using Zenoh, which was quite interesting and quite good for us. In terms of raw performance, because it's not just wire efficient, it's extremely performant. These are number of messages per second over 100 megabit per second network running on top of IP. So you see we hit 4 million messages per second, but more interesting diagram is this one. You see that in dashed line, that's iPerf throughput, which is around little bit less than 60 gigabit per second, and we arrived to 56 gigabit per second at roughly 16 kilobyte payload. We saturate a gigabit network by memory, it's 32 byte, and 10 gigabit network at 512 byte payloads. So you can imagine we play lots of tricks in terms of batching and network scheduling. Zenoh versus MQTT, no story, okay? So you see the difference here. So let's jump quickly to the abstraction before we then go to the conclusion. So when we built Zenoh, what we really did was to merge two concepts, okay, and try to marry two concepts. State-of-the-art PubSub protocol and state-of-the-art NDN. I don't know if any of you is familiar with NDN. NDN stands for Named Data Networking, and was a family of protocol that in my research community, we were coming up as proposal for next generation Ethernet. I don't know if any of you know Louis Pouzin. He's one of the guy, polytechnician, who invented essentially datagram networks. So he's really the father of the internet. Then he went to work for MIT, but he's back in Europe. So we have two initiatives, one in Europe called NGO, Next Generation Internet, and one in US run by Stanford, where we were both looking at this kind of protocol that make it very easy to query data over large-scale networks. But the problem before Zenoh was that you could either have protocol that could query data over a large-scale network using location transparency, or you could very efficiently distribute data. And if you were trying to do the same with the same platform, it was horrible. And so we have successfully married the two, okay? So we continue to embrace the named data principle. So the big difference is that, in the internet days, the network is host-centric. So you need to know the address of the host. In data-centric network, you don't care about the host. You care about data, and all of your data communication is driven by naming the data, okay? So here you have example of naming a specific data sample, which we call resource, or providing wildcards to indicate a set of data you're interested in. Notice that, as you will see, when you do a query or when you express a subscription, you don't need to know where the data is stored or how many places store the data or what is the closest place. It's our routing protocol that figures that out, okay? In terms of selecting data, obviously you can select the set of keys that represent the data you're interested in, and then use predicates, for instance, to say, look, among the temperature sensors in my house, please get me only those whose value is greater than 25. Or perhaps in my car dynamics, for the speed, please, whenever the speed is greater than 25, just project the acceleration. That's the only attribute I'm interested on. Okay, quickly moving to the primitives. As I said, we have 4 primitives. So you have a resource, which is nothing but a key and a value. Then we have a publisher, which you can think of it as a spring of value. A publisher commits to produce value, okay, whose key match a given expression. You have a subscriber, which you can think of it as a sink. So a subscriber in the network tells, look, whenever there is some publisher that publisher a resource whose key matches this expression, please deliver to me. And then we have something that we call queryable. What is a queryable? A queryable is like a well. A well is a place where you go with a saw looking for water, right? So what the queryable promises you is that, look, if you're looking for any data whose key matches this expression, you can come to me. But then how the queryable will respond to your query, you don't know. So it could be a computation, it could be a storage, it doesn't really matter. That's an implementation detail. And again, that's up to the higher layer to decide whether it's a distributed computation or it's a storage, okay? And with these 4 primitives, we can express everything, okay? These primitives are understood by the protocol. These endpoints are discovered by the protocol, okay? And we route to them based on a naming data net protocol. Then in terms of primitive, obviously, you can scout. We have open and close of session where we negotiate lots of things, okay? And then in terms of the operation to manipulate it, you can put a resource, you can get a resource, which is a distributed query, or you can pull, where pull allow you, if you're a device that sleep, to say, look, I want to receive data, okay, but you know what, get this data as close as possible to me, and then I will tell you when I'm ready to consume, but you please get it as close as possible to me. Okay, then we provide higher level concept like storage, where a storage is actually the combination of a queryable and a subscriber. And as part of our platform, we provide plugin for off-the-shelf storage technology. So all of a sudden, you can federate, MySQL, MariaDB, Cassandra, InfluxDB, you name it, and access them in a location-transparent manner by using our protocol. Because again, we didn't want to reinvent storage technology. We wanted to federate and make them accessible in a location-transparent manner. And the plugin API is extremely simple, so it's quite straightforward to add a new model. Wrapping up, in terms of communication topologies, we support peer-to-peer, right? We support broker communication, and in general, this is the topology that you can deploy. So you can have, we have multi-domain routing, because that's essentially if you are deploying internet scale, and we have customer doing robotics, teleoperation, and management that have robots across a country, and so we have an infrastructure deployed in place. And then when you see the peer could be robots communicating peer-to-peer, and then eventually being teleoperated by an operator that is on the other side of the world, and so on and so forth. So putting it all together, just to give you a glimpse of how this works, let's assume all of a sudden now we are enjoying a visit at the Louvre, because being in Paris, that's a nice place to be. And let's assume for some reason that we wanted to store the data produced by sensor at every floor of the Louvre in a separate database, okay? So you see that we have 2 storage, one that will store all the data whose key starts with Louvre 2, where 2 is the second floor, and for simplicity we have another one on the top right corner, which store all the data Louvre 1. So whenever there is a publication, right, in this case it's a publication from a temperature sensor in room 42 on the first floor, then all subscribers that are interested in that publication receive it, as well as storages who have an expression that matches that key. Okay, so that's the writing side of the storage. Now another sensor writes some data. So again, that's received by relevant subscriber. And notice that there is a subscriber sleeping. That's a pool subscriber. So Zenoh is caching the data for this subscriber as close as possible. And where it's cached is the infrastructure they decide depending on resources and topology. And as soon as this node wakes up, it just says, hey, ready to consume so much data, okay? Zenoh gives the data, and once you've finished consuming all your data, that's garbage collected. And that's very important, because if you have only push technology, how do you deal with devices that sleep? Okay, and now suppose that actually I wanted to get the temperature for room 42 across all floor. Well, easy to do, because you express the data you're interested in. And in that case, essentially what our protocol does, it computes a set cover. Okay, so in terms of set operation, identify the minimal set of storages around the network that can answer that query, typically the one that it can reach with the least cost, submit the query, and then consolidate back the result. And whether the storage are, one step away from you, whether they are across the globe, whether there is 1 or 10 or 1 million, doesn't matter for your application. And so you decouple completely the location, the replication, the scale out, okay, because load balancing becomes trivial. Okay, so in terms of application domain, we're used a little bit everywhere. I think the latest, besides the India Autonomous Challenge, which is very cool, there was Deutsche Bahn that recently demonstrated the first automotive train using Zenoh within the train and for train to infrastructure. For those of you that speak German, I have the TV interview in German. And so wrapping up, okay, in time, I believe. So Zenoh is open source, it's innovative, I think very innovative. Very often we think that innovation happens across the Atlantic Ocean, but I think there is actually a lot of cool things that happen in Europe that few people know about. It's not only fully European, but it's actually, this technology is built on the plateau de Seclet. So our lab is just 100 meters away from Centrale Supélec, and we actually work quite closely with most of the Grande École and universities across the globe. So if you want to try it out, feel free to check it out on Git. There is our website, and we have a very, very active Gitter channel where you are welcome to ask questions. Our community is super supporting and welcoming. So thank you very much. So we'll finish with a quote of the day. And by the way, I'll distribute the slides, and those who know me, I always show some code. But I didn't have the time, but you still have the code in the appendix, so don't worry, okay?
Okay. Do we have a question in the room? Okay, good. Wait.
Canvas? Canvas, yes. Okay, so... Yeah.
Does it work with Canvas?
So good question. We don't have Canvas as a transport right now, but it's just a matter of doing a transport plugin. Just to give an example, we support ThreadX because that's being used by some interesting robots in some application. So, and again, what would be very interesting about Canvas is that Canvas, for those of you that don't know, it's a field bus, which, by the way, uses a very smart collision detection and avoidance, leveraging Open Collector. Anyway, this brings long memory, yeah? But you have essentially priorities, right? And in Zenoh, we actually have traffic prioritization. So you can associate priorities, and though it would be very nice to, or very natural to map Zenoh priorities into Canvas priorities. So in short, okay, if we go back to the diagram with the stack, transport are pluggable. So it would be as simple as doing a transport plugin for us. No problem at all.
I think we have no more questions, so we can applaud.
Thank you. I hope that was interesting.
Yes.